Without further ado, please welcome with warm round of applause, Professor Walter Lewin.
During my last lecture, we discussed the gravitational acceleration due to the Earth. And I told you that the gravitational acceleration due to the Earth is called g in physics, and that it is very close to 9.8 meters per second squared. It varies a little bit over the Earth, but not very much. At that time, I also told you that if you drop an object with zero speed and you let it fall, that its speed will increase according to this equation. We had that on the blackboard last time. V would be in meters per second, T would be in seconds, and G would be 9.8. I now want to make a plot of this V versus T in the same way that I did last time, just to warm you up a little. This is T, will be in seconds, and this is the velocity, which will be in meters per second. So if I drop an object, so here, I drop an object from point A, and it's falling down, and I give it no initial speed, then it will follow the following curve. It will be a straight line. The velocity in the beginning is 0, and every second it will increase by 9.8 meters per second. So after 1 second, the speed is 9.8 meters per second, and after 2 seconds, the speed is twice that. The speed doubles. It's going to be 19.6, and so on. After t seconds, a random number t, the speed of that object falling down will be gt, because v equals gt. What we did not discuss is how far does it move in 1 second. Neither did we discuss when it hits the ground, what is the speed at which it hits the ground. I'm going to explain to you how far it moves in 1 second. But in order to do that, I'm first coming down to the world that you are so familiar with, which is your own car. Here is t in seconds, and here is the velocity of your car in meters per second. You're driving at a constant speed. That's why the line is horizontal. It's not changing with time. But then at one point you decide, well, I go a little faster, so you accelerate, and then again you end up going with a constant speed. And this original constant velocity is v1, and the second one is v2. And this is in meters per second. Let us assume that v1 is a reasonable speed. Let's say we take 60 kilometers per hour. But we have to convert it to meters per second. So that happens to be 16.7 meters per second. So how far does that car move in 1 second? Well, that's a no-brainer, right? It goes 16.7 meters per second, So in 1 second, it goes 16.7 meters. So in 1 second, it goes 16.7 meters. Let's now take a look at this plot. A physicist would do the following. A physicist would draw a line here and would draw a line here. Well, most can't make such nice dotted lines, but that's a different story. And they take 1 second. And they say the area of this rectangle is 1 times V1. So the object moves V1 meters per second. This is V1. And so it can do the same here. 1 second. You take the area under here. This is V2. This is 1. So in 1 second, the velocity here will be V2 meters per second. So in 1 second, the distance that it will move is V2 meters. So what we in physics do, we calculate the area under the line. And that area indicates then the distance that it has moved in 1 second. We go now to this diagram. Suppose the object was falling down all the time with a speed vgt. Well, then you would have to take the area of this rectangle, and that is gt times t, so that is gt squared. But that's not what the object is doing, because the object is doing this. The object is increasing its speed. And so this triangle is exactly half this area, and so the distance that it has traveled is 1/2 gt squared. And so now we have a new important equation, that the distance that this object moves, if it is in free fall, equals 1/2 gt squared. We can take an example. Let's calculate how far it moves in 1 second. Well, in 1 second, t squared is 1, g is 9.8. So in 1 second, it moves 4.9 meters. It falls 4.9 meters. But of course, its speed is 9.8 meters per second. Because t is 1, so the velocity is 9.8. But at least now you know that it has traveled, it has moved only 4.9 meters. Suppose we allow it now 2 seconds to fall. Now the t squared becomes 4. And therefore the distance that it travels now is going to be 4 times this, because of the t squared. So what I've calculated for you is this distance now. You tell me what time it is, and I will tell you then how far it has moved. Now, we're going to ask ourselves the following question. Here is the ground. We call this point B, and this distance from A to B is 8 meters. How long will it now take to reach the ground? Well, that's very simple, because D is now h. So now you get that h equals 1/2 gt squared. So you tell me what h is, and I will tell you what t is, or you tell me what t is, and I will tell you what h is. If you tell me what the h is, then t, now this is very difficult algebra now what I'm going to do, t is then going to be 2h divided by G, and then the square root. If you can't follow that, you just have to accept it. But it's the result of this equation. So now we can take a very simple example. We will take h 100 meters. H is 100 meters. We go to that equation, and we ask what t is. We put in 200 divided by 9.8, and we find that t equals 4.518 seconds. I did that with my calculator, and you should be able to do that too, of course. But now that we know how long it takes to hit the floor, I go to this equation, and I now know the speed at which it hits the floor, because I put that t in that equation. So I also know now that the velocity is then going to be 44, is it 44? Yeah, 44.27 meters per second. So we know now how long it takes, and we know the speed. 44 meters per second is very close to 160 kilometers per hour. So that means if you were to jump off a tower, if we ignore air friction, if we ignore air drag, then you plunge to the floor and you hit the ground with 160 kilometers per hour. That's a typical number if you jump from a 100-meter tower. Now that we are so far, suppose the mass that I drop is 1 kilogram. Then I can also calculate, as we did last time, what the difference is in potential energy between point A and between point B. This is the ground. We will give this arbitrarily potential energy 0, and then the potential energy A is higher by the amount mgh. Perhaps you remember that. So the potential energy at A minus the potential energy at B is m times g times h. Last time I wrote on the blackboard m times h times g, which is exactly the same thing, of course. And so, if m is 1 kilogram, if h is 100 meters, if g is 9.8, then this is 980 joules. So that is the potential energy at point 8. I now would like to do an experiment which is not an easy one. I would like to measure with you the gravitational acceleration right here. We all know that MIT is the center of the universe. So therefore, if you want to measure the gravitational acceleration, you might as well do it at MIT. And how am I going to do that? Well, look, for instance, at this equation. I can bring g out. So g equals 2h divided by t squared. So if I have a known height, which I do, which is there, that height is 3.000 plus or minus 0.002 meters. In other words, we know the height only to an accuracy of 2 millimeters. So I know h. If I can determine now how long it takes for that object to fall down, then this equation will tell me g. The instrumentation is extremely sensitive. And so there is a chance that it may not work out as well. But that's part of physics. Bill is now going to place a ball right at the top there. And then we will let the ball fall. And at the floor is a switch. And the two talk to each other. When the ball is released, the timer will start. you see the timer there. And I will dim the light a little so you can see the timer well. We know the time then that it takes from there to there. The moment that it hits the switch on the floor, the timer will stop. And then this equation will give us the result for G. Just imagine what an historic moment this must be in your life. As far as the timing is concerned, if everything works well, then we know the time to an accuracy of 2 milliseconds. No better. So, I'm going to set the timer at 0. Bill, I know you don't trust me when I pull that string. Why don't you pull the string?
Sure.
Yeah, why don't you pull the string? If I pull the string, the ball is supposed to fall. 7795. 0.7795.
99.
Oh, excuse me. Can I take a look?
Yes.
Oh, that's even better. $7,799. Now hold your breath. I'm holding my breath too. So we get 6, because 2h is 6. 0.7799, 0.7799, and we find 9.86. Well, G equals 9.86. Now comes the $64 million question. What is the uncertainty in this number? I almost always leave something for my students to be done. And so I want you to calculate what you think the uncertainty is. Remember, there is a 2 millimeter uncertainty in the height of 3 meters, and there is a 2 millisecond uncertainty in the timing. I will give you the answer, and then you can check whether you come up with the same result. It turns out that the uncertainty is plus or minus 0.05, and then we get meters per second squared. We know that the gravitational acceleration at the center of the universe is very close to 9.80. And that is within the uncertainty of my measurement. So that's why I said this is a historic moment. You remember you saw last time the astronaut on the moon who dropped a feather and a hammer, and they fell, and he did that to show that they hit the surface of the moon at the same time, in honor of Galileo Galilei, who was the first person to suggest that. It only works in vacuum, and that's why the astronaut did it on the moon. The gravitational acceleration on the moon is 6 times lower than the gravitational acceleration on Earth. So you can ask yourself now the question, how much longer does it take for an object to fall on the moon compared to on Earth, if you drop them from the same height? Well, this is the time that gives you the answer. And G on the moon is 6 times lower than on Earth. So if you are very poor in algebra, then you would say, okay, then the t is therefore going to be 6 times longer. So it will be 6 times longer to fall. But then you overlook the square root. So it is not 6 times longer, but it is the square root of 6 times longer. So it's 2.5 times longer it will take on the moon. And you may remember when you saw that video that I said to you, watch carefully. It falls clearly slower than what you're used to. So we know that it takes 2.5 times more time than on Earth. How about the speed with which it hits the surface of the moon? Well, this equation. G is 6 times lower on the moon, so it's reasonable to think that the velocity is then also 6 times lower. So now you make again a big mistake. You make one mistake after the other, I told you that. Because the time is 2.5 times higher, and if G is 6 times lower, then the velocity with which it hits the surface of the moon is not 6 times lower, but is 2.5 times lower. So now you understand those equations, even if you apply them on the moon. I'm going to return to my case, whereby I have h equals 100 meters. Where is that? That is here. The object falls over a distance of 100 meters, and we know that the gravitational potential energy difference between A and B is 980 joules. As it falls, it increases in speed, goes faster and faster and faster and faster. Here you see goes faster and faster and faster and faster. And then it hits point B, and then it has a high speed. Speed in physics means energy. We call that energy of motion, for which we have invented a name, which we call kinetic energy. And kinetic energy, something that I will not prove, although I do prove that, of course, in my physics classes, kinetic energy equals 1/2 m times v squared. So when something has speed, it has kinetic energy. If it has no speed, no velocity, it has no kinetic energy. Well, we had an object of 1 kilogram, 1/2. We multiply that by 1. And we know what the velocity is. We already calculated that. When it reaches that point B, this is the velocity. But in the kinetic energy, you have to square it. And so this now is the kinetic energy when the object reaches point B. And what do you think that number is? If you have a calculator, that number is 979.9 joules. What an amazing coincidence. What a coincidence. All that energy that was originally available in terms of gravitational potential energy is now converted to kinetic energy when the object reaches point B. And that now is at the heart of the holiest law of physics, which is the conservation of energy. So, you see now that the potential energy at point A is the kinetic energy at point B. If I write this down in a more general term, then I can write down that the potential energy at A plus the kinetic energy at A is the same as the potential energy at B plus the kinetic energy at B. Now, we agree that if the object is at A, it has no speed because we drop it with 0 speed. So this term is 0. We also agree that when the object is at point B, that the potential energy is 0 because all the potential energy, remember, was in A. So this is 0. So you see that the conservation of energy gives you immediately the result that we already knew. However, the conservation of energy is so uniform that if I pick a random point P on the way down, then the sum of the potential energy and the kinetic energy of that point P is exactly the same as this and exactly the same as that. And now you see the conservation of energy in its most general form. If I go back to that amazing coincidence, I will rewrite it. That amazing coincidence that mgh equals 1/2 mv squared. Remember, this was the 100 meters. This was the 1 kilogram. This was the potential energy at A. This is the kinetic energy at B. So I can also write it down in this form. And then you see another miracle. This m and this m can be divided out. And so now I see something incredible, something earth-shaking. I see now that v, which is the speed, equals the square root of 2gh, if your algebra is good enough. You bring the 2 to the left side, and then you get that v is the square root of 2gh. So now you have an equation whereby all you have to know is what the height over which something falls, and you find immediately the velocity. So what do you think? If I put in this h, if I put in 100 meters, what do you think v will be? Don't use your calculator, that's cheating. What do you think if h is 100 meters? What will this equation tell you about v? Come on, behave like MIT students. Of course, it has to be the 44.27 meters per second, which we calculated in a different way. And believe me, if you are at home and you have your calculator, use this equation and you'll find you 44.27 meters. But the beauty of this equation is, it reminds me of Galileo Galilei. He said, it makes no difference what the mass is of the object. This equation says, indeed, it makes no difference, because there is no mass in this equation. All you have to know is the height over which it falls, and I will tell you the speed. It's the same for all objects. So that equation also gives you a nice insight. If I summarized now the situation, then we have a pretty full understanding of falling objects that we release with 0 speed. We know for one thing that any mass comes down with the same speed. We can calculate the speed now at any moment in time. We can calculate the distance that it travels at any moment in time. We can calculate the potential energy of any point at any moment in time. We can calculate the kinetic energy at any moment in time. And of course, we realize day and night, even at 3 o'clock in the morning, that there is always the conservation of energy. I want to show you a very interesting demonstration. Not earth-shocking, but it makes you see something in a very nice way. We have an object here. It's a nice white ball. Where do we have the ball, Bill? We can show it. Here's the white ball. And we're going to put this ball way up there. And we're going to put it about 3.2 meters above the ground. It's not necessary that I tell you the uncertainty because it's irrelevant, whether it's 3.2 or whether it's 3.1 or 3.3. You will understand shortly why. And then we're going to let it fall, free fall. But while it free falls, we make it completely dark in the room, and we're going to strobe it with a strobe light. But the distance between the strobe lights, the distance between the time that the lights go on, the time distance is, of course, the same. So the first time that the light goes on, it has only fallen a very little bit. The second time that it flashes, it has fallen way more. And the third time, it has fallen even more. And you are going to look at that. And I'm going to ask you, when we do that experiment, how many of these balls did you see during the time that it was dark in the room and that you saw those balls? I can already tell you that the experiment will only take roughly 0.8 seconds. Because if you put h equals 3 meters, if you put that in this equation, then you get a t of only 0.8 seconds. So the whole thing goes very fast. But during that time, I'm going to strobe it. And I want you to tell me how many of those balls you saw. And I will help you a little bit, as I always do with students. Suppose the strobe was strobing at 5 hertz. That means 5 times per second. Then between the light flashes, there would be 0.2 seconds. But it takes the ball 0.8 seconds to fall, so you could only see the ball 4 times. A time takes 0.8 seconds. Every 0.2 seconds you get a light flash, so you could only see 4 balls. So if you tell me how many balls you see on the way down, not only will you see, of course, that the distance increases, but you can even tell me then what the frequency is of my strobe. And so Bill and I both have to work on that. We made a deal. Oh, come over, Bill. The deal that we made is, Bill was first going to put up this beautiful piece of velvet so that the background of the falling ball will be very dark. We will remove this after this demonstration. It's only for now. All right, so that's almost in place now. Perfect. So Bill is now going to set up the camera. It's a Polaroid camera. And then we will turn on the strobe. But Bill gave me a task of immense responsibility to put the ball up there. So Bill, work on your camera. Okay. I will move this out of the way. We're going to make it absolutely dark. And Bill and I have worked out an extremely sophisticated method of synchronization. Very high tech. Because the camera, the shutter of the camera has to be open during those 0.8 seconds. If the camera is not open during those 0.8 seconds, then obviously you will not see all these balls. So we invented a method that we are very proud of. I am going to count 4 seconds. 1, 2, 3, 4. At 3, I will drop the ball. Between the 2 and the 3, Bill will open the shutter of the camera, and when I say 4, he will close the shutter. Now, if that is not high-tech, I wonder what is. However, it is important that when I count 1, 2, 3, 4, that I really count seconds. And therefore, Bill and I are now going to calibrate our memory what a second is. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I will remind you that I will drop the ball at 3, and that Bill will open the shutter just a little bit before that and closes it when I say 4. So we know for sure that we have the crucial 0.8 seconds on the film. 1, 2, 3, 4. Bill, are you ready?
I'm ready.
This is going to be for real, Bill. You ready?
I'm ready.
1, 2, 3, 4. Now I'm very curious what you saw. And I would like to know who saw more than 5 balls? One person. How many did you see?
7 or 8 maybe?
Excuse me?
7 or 8.
7 or 8. Who saw fewer than 5? How many did you see? 3. Who saw no balls at all? Well, it takes 30 seconds for this film to be developed. And so we will see. The film will tell how many balls we see, and then I will tell you also what the frequency was of my strobe. And of course, the two have to agree with each other. So Bill is now getting ready for the final result. It's always nice that we are the first to be able to look at it. Oh, ha, ha. You see a big smile on my face. This is fantastic. I'm going to make it dim 5 again, or dim 6, right? Can you get me the... This is turned on already, right? That's what you saw. Our strobe was 10 Hertz. And that means there is a flash every 1/10 of a second. And it takes 8/10 of a second to fall 3 meters. So you should see 7 balls. In an extreme case, maybe 8, but 7 is more likely. Okay. This one you really may not want to count because it may have been flashing already when the ball was not falling. So 1, 2, 3, 4, 5, 6. That happens. The first one may actually be hiding behind this one. And if you want to count this one, that was number 7. Who saw 7? Well, you were lucky. But of course, my goal really was to make you see that this distance is smaller than this distance, and that the distance in time increases. Which is, of course, exactly what you expect. So far, we have only dropped objects, releasing them with 0 speed. But now I would like to throw an object up from point B all the way up to A, and I want it to come to a halt at point A. And I ask myself now the question, what is the speed that I should give it in B so that it comes to a halt at A? And now what you use is, of course, the conservation of energy. You know that the potential energy plus the kinetic energy here is the same as the sum of the potential energy as the kinetic energy there. And so therefore, if the object falls down and you know the speed with which it hits here, if you would shoot it back up with the same speed, it would reach point A again. That would be completely consistent with the conservation of energy. And so the beauty of this is that once you know at what speed it reaches B, to get it back to A so that it stands still here is exactly that same speed. And that is the beauty of physics. It is the simplicity, it is the symmetry in physics. If it takes 4.5 seconds over 100 meters to fall from A to B, it will take 4.5 seconds to go back from B to A. There is an incredible symmetry. I have here a tennis ball. And I throw the tennis ball up about 1 meter, and I catch it. I throw it up 1 meter, and I catch it. Does it surprise you that that works? Or do you think this is just a boring demonstration? Does it surprise you? It takes half a second to go up and half a second to go down. You should be able to calculate it because you can put in there, if h is 1 meter, it takes about half a second to go up. But now, let us suppose that I do this demonstration when I'm in an airplane. Here's my airplane, and my airplane is with a constant velocity going in this direction, and here's Walter Lewin, and I throw the ball up, vertically up. Will I now be able to catch the ball? Or will the ball say, sorry, you're going with 550 miles per hour, 800 kilometers per hour. I'm not going to stay with you. I'm going to do this. And I could never catch the ball. But that is strange. Because I don't even know that I have this high speed. The windows are closed. It's a very smooth ride. As far as I'm concerned, I'm not even moving at all. It feels as if I'm standing still. So I would expect if I throw up the ball, that it would come back and that I can just catch it. Can the ball tell me that I am going with such a ridiculously high speed? There is no way that the tennis ball can tell me that I am moving. If it could, that would even be a violation of Einstein's theory of special relativity. I'll tell you a secret. Without you knowing, you are all, at this moment, in a supersonic airplane. All of us in the lecture hall, are moving with a near constant velocity of 100,000 kilometers per hour. Because that is the speed with which we go around the sun. 100,000 kilometers per hour. And when I threw the ball up here, there was no indication whatsoever that we were going 100,000 kilometers per hour. So now that I tell you this, maybe this wasn't such a boring demonstration after all. Maybe it is surprising. Now, seeing is believing, and I'm therefore going to make you see in a different way that may be a little easier for you to remember, and that will make a believer of you. You think that this is a car. It's not. It's an airplane. And I am inside that airplane. It's a mini version of Walter Lewin. And I'm going to throw a ball up in the airplane and see what happens. Now you can notice that the airplane is not moving. And the reason is that people are still boarding. But I am already in that airplane. So I could throw the tennis ball up 1 meter, and of course you can predict what happens. The same thing what happens here in 6120, because the airplane is standing still and I'm standing still, so this is what you're going to see. Oh, I didn't throw it up vertically enough. Thank you very much. So something like this is what you're going to see. So the plane is not moving, but I'm in there, and indeed, the same thing as in 6120. But maybe not so boring anymore. Now, very soon, the plane is going to fly at a speed of 800 kilometers per hour. And then I will throw the ball up again when I'm strapped in my seat. And I will demonstrate that if I throw the ball exactly vertically, that I will always see the ball exactly above my head. And even when I'm strapped in my seats, I will be able to get the ball back. So that means when I am in that airplane, I will indeed see this. But that's not what you will see. See, you are not allowed to take the plane ride with me. And so you will see something very different. For one thing, you will see the plane move. But you will also see that I catch the ball. That's non-negotiable. And that's so interesting. And that's what I want to show you. What is it that you will see? I have to make a small change because in order to throw the ball again, when I'm sitting in the airplane, I have to first take the ball out of here. Which is always a little difficult. There it is. All right. Now I'm going to tell you what I will do. The plane will start to taking off 800 miles per hour, 550 miles per hour, 800 kilometers per hour. I will make it do that. When it goes over this point, I'm sitting in the plane, I decide to shoot up the ball. And then the plane takes off. And then you will tell me what you see. You must see the plane move, but you must also see me catch the plane, catch the ball. Now, this is a tricky experiment. I have to make sure that it goes over this point. This is, yeah, looks good. Looks good to me. So are you ready?
Yeah.
1, 2, 3. Ooh. I shouldn't have that drink in the plane. I didn't really throw it exactly vertically off, but I threw it a little bit at an angle, and so I couldn't reach it. You want to do it again, Bill, or shall we just leave it with that? You want to try? What do you mean, try again? It worked beautifully. The fact that I had that Bloody Mary is not the fault of the experiment. Well, you took the ball out? It's very nice of you. It doesn't want to latch at... Okay. Well, let's see. Okay, last try. 1, 2, 3. By the way, this arc that you have seen for the mathematicians in my audience is a parabola. So I hope that I have convinced you now that whatever constant velocity I may have in my moving frame of reference, that physics works in the same way. That there's no difference between my not having any velocity or my having a constant velocity, even if it is as high as 100,000 kilometers per hour, all of you. When you come to think of it, that is intriguing, isn't it? I now want to discuss with you a situation where the reference frame is not moving with a constant velocity, but with a constant acceleration. This is the ground, and here is a tree. The top of the tree is an animal, it happens to be a monkey, and the name of the monkey is Robert. There is a nasty hunter who wants to shoot the monkey, and he has a gun here which is aimed exactly at the monkey, and he gives the bullet a speed v. At the moment that the bullet is fired, Robert sees the light flash of the gun, and he lets go. That means he falls out of the tree. In the absence of gravity, this would be exactly the trajectory of the bullet. We would call that the zero gravity trajectory. But there is gravity. And Robert and the bullet start to accelerate downwards at exactly the same time. And when Robert has fallen over a distance d, the bullet has fallen exactly the same distance d below this line. So, when Robert is here, and when this distance that Robert has fallen is this much, the bullet must be the same distance below this line. Therefore, the bullet has to be somewhere on this dotted line, which I draw parallel to this one. Let's assume the bullet is here. Then, this distance is also d. If Robert has fallen 40 centimeters, the bullet will have fallen 40 centimeters below this line. If Robert has fallen 1 meter, the bullet will have fallen 1 meter below this line. The distance d is always the same for both. It is that famous 1/2 gt squared. Thus, from Robert's frame of reference, the bullet keeps coming always from the same direction. And therefore, the bullet is coming towards him along a straight line, and that is independent of the speed of the bullet. I'll now make a diagram whereby we put in the trajectory of the bullet. So let this be the trajectory of the bullet, which, by the way, is a parabola. I'm now drawing here 2 parallel lines, parallel to this one. I draw them at random. It doesn't matter where I draw them. Now comes something very important. At the moment that the bullet is fired, this is where the bullet is, and this is where Robert is. A little later in time, when Robert is here, he has fallen over this distance. That means the bullet must then be here. This is that same distance. A little later in time, when Robert is here, the bullet must be there. Robert has fallen this far, and the bullet has fallen exactly that same distance. And so now you see what happens when Robert is here, the bullet is there at exactly the same time, and so Robert will get killed. It's very tragic, but Robert will always get killed, independent of the speed of the bullet. If the speed of the bullet is high, Robert is going to be killed somewhere here. If the speed of the bullet is low, Robert is going to be killed somewhere here. If the speed of the bullet is very low, then Robert may not be killed at all, because the bullet may never reach Robert. If Robert had not let go when the gun was fired, he would have survived, unless the bullet would have an enormously high speed. But since he let go, exactly at the same moment that the gun fires, he's doomed. This is very sad. But the good news is that one of the first things I did when I came to MIT 46 years ago, I gave Robert a bulletproof vest. I will now go and get Robert. You must understand that this is a very emotional day for him. So please treat him with respect. I got Robert. I don't go hunting every day, but when I do it, I want to do it in style. So, Robert, I'm going to put you up here. The switch down there. So Robert is going to be hanging here on the top of the tree. Oh. Robert doesn't like the experiment. You can't blame him. You may just have noticed that Bill is checking very carefully that the gun is aimed exactly at Robert. Robert, I apologize for that. I really mean it. But your bulletproof vest will save you. I have to cock the gun. Put in the bullet. Bye, Robert. I hope to see you Monday.